Let's discuss principal stresses. Before that, what is principal plane? So it is the plane on which there exists only normal stresses. That means no shear stresses. And these normal stresses are called principal stresses. So let's try to understand this. We know we can define traction at a point, okay, with respect to some reference surface normal. Okay, so let's check this is the traction on this cut plane or with respect to this reference surface, and this surface can be described by its normal n. Now this traction generates or this traction gives us some stress components sigma ij. Let's take there sigma ij. Now we know at this point there exists infinite number of planes, right? So if we take let's say this particular plane, okay, and if we define the traction on this plane, okay, it will give different stress components because the reference coordinate system is also changing. Okay. So we get a different stress components. uh, that means at a point we get infinite number of stress components if we change uh, the reference surface normal. Okay. Now, out of this infinite stress combinations, okay, there exists a particular plane, reference plane, where the traction gives only the traction gives only normal stresses. Okay, there are no shear stresses. Okay, and this particular plane is called principal plane, and those normal stresses are called principal stresses. Okay. Hope this is clear conceptually. Okay. Now let's find out how to get the principal stresses. Okay, so we have seen this in previous section. Okay, it is a relationship between traction and stress state. Okay, and this particular stress state we can say it is arbitrary state. So it is very general stress state. Okay, so we can say it is arbitrary stress state. Okay. This is a relationship between traction and arbitrary stress state. Now we want to find the principal stresses from arbitrary stresses. Okay. So we know like those arbitrary stresses will become principal stresses at one particular plane. Okay, that is principal plane. Okay, so let's take that particular plane is LMN. Okay, this LMN is principal plane. Okay, and so we say that traction will have only normal stresses on this principal plane, right? And this stress state, okay, on this principal plane we can define describe it as a sigma p sigma p sigma p. Okay, sigma p is a principal stress and other components are zero because it is a principal stress state. That means the shear components are zero, only diagonal components are available, which are normal stresses. Okay, so these all diagonal normal stresses are called principal stresses, and this in form of matrix or state stress state we can describe something like this. Okay. So this is arbitrary stress state. Okay, may please note this difference, and this is a principal stress state. Let's move. uh, so once we have said okay this is a principal stress state, okay, we can use our relation between traction and arbitrary stresses, okay, to get relation between traction and principal stresses. So this is our from previous section. Okay, this is in matrix form. in form of equation. Okay, this is our relation between traction and arbitrary stress. Okay, so uh, for principal stress, okay, this is zero. This shear are zero. All shear components are zero, and we will have only these diagonal components. Okay, sigma 1 1, sigma 2 2, and sigma 3 3, which are principal stresses. So I can say T1 is equal to sigma PL, T2 is equal to, this is 0, sigma PM, and T3 is equal to sigma PN. Okay. So that's what I have written here. So relation between traction and principal stresses are T1, T2, T3. So this is just derived from this. Okay. We have made all these shear components as 0, and sigma 1 1 will be now sigma P, sigma 2 2 is also sigma P, and this is also sigma P. So this is our relation between traction and principal stresses. Now we want to find the principal stresses from arbitrary stresses. Okay, we know the arbitrary stresses will become principal stresses on a principal plane. So we can say that no, we can equate the tractions coming from arbitrary stress state, okay, with the tractions from principal stress state. Okay, so both are going to be same. So we can say, okay, these T1, T2, and T3, which is in form of arbitrary stresses, will be equal to these T1, T2, T3 from principal stresses. Okay, so this one, okay, or in equation form, if you see these all three equations, right hand side, these are right hand side of that relation between traction and arbitrary stresses. They are equal to these stresses. Okay, so we are just equating T1, T2, and T3 from arbitrary and principal stresses. So we get these three equations. Now we have principal stresses on right hand side and arbitrary stresses on left hand side, and so our objective is finished, right? We want to find the principal stresses from arbitrary stresses. Okay, so let's just expand this. The remaining is just expansion of these mathematical equations. So this one we can also write it in matrix form. Okay, we know the matrix multiplication rule. Okay, this equation will be sigma p into L. Then this multiply with this will be equal to sigma pm. Then this third row multiply with this column will be sigma pn. Okay, so we get this. So this is both are same. Okay, this is in algebraic equations. Okay, and this is in matrix form. Both are same. Similarly, we can write same thing in tensorial form also. So all these three form, both three all are same, okay, same, but in a different form. So this is in tensorial notation, okay, where this sigma is a stress matrix, okay, into direction cosine dot n is equal to sigma p n. Okay, this just note this, here I have put dot, here there is no dot because sigma p is scalar. Okay, it is just simply multiplying with this vector direction cosine, and this is matrix multiplication, so sigma dot n. Okay, and this dimension wise is also same. Sigma we know it's a 3 by 1, this vector is 3 by 1. Okay, this is a scalar, and this n is 3 by 1, so here we get 3 by 1. Okay, so 3 by 1 equal to 3 by 1. Anyways, so this is for additional information. Okay, but let's focus on this. Okay, now let's expand this further to find the principal stresses. Okay, uh, okay, I can write this, I can keep this in left hand side, I can move this to left hand side and right hand side is 0. Okay, and further doing that we get this matrix form. Okay, so I have what I have done, minus sigma p equal to 0, minus equal to 0. So we have just moved it to left hand side. Okay, and this one now in matrix form can be written like this. Okay, you can check this one. Now this equation, okay, it is if we say like L equal to M equal to N is equal to 0, okay, it gives a trivial solution. That means we cannot solve this equation. That means this should be 0. Okay, so the determinant of this matrix is a 0, is the solution of this equation. So the determinant of this matrix is equal to 0. uh, Further expanding, okay, in uh, equation form, okay, we get this equation sigma p cube minus I1 sigma p square plus I2 sigma p minus I3 equal to 0. Okay, so this is a cubic equation, and this equation, okay, has three roots. Okay, so if we find sigma p is unknown, so if we find the roots of sigma p, we get three roots: sigma 1, sigma 2 and sigma 3. These are called principal stresses. Okay, just note the uh, this convention. Okay, it is sigma 1, sigma 2 and sigma 3. Here arbitrary stresses are sigma 1 1. Okay, 1 1, 2 2 and 3 3. So here we are using a 2 index. Okay, but for principal stresses, it is just simply sigma 1, sigma 2 and sigma 3. So this is the difference. So always no principal stresses are written uh, in order of largest magnitude. Okay, so sigma 1 is always greater than sigma 2. Okay, and this is always greater than sigma 3, and this one is max principal stress, this is minimum principal stress, and this is mid principal stress. Okay, and in coming chapters, okay, in future chapters we will see the significance of maximum and minimum and this mid principal stresses. Okay, so this is how we get principal stresses from arbitrary stresses. So we have been given some arbitrary stresses, okay, some values, and using this equation we can find the principal stresses. Now we have to discuss about this I1, I2, I3. So this I1, I2, I3 are called invariants of stress matrix. Okay, say stress matrix sigma ij. Okay, what is, what does it mean, like invariance? Invariance means they do not change with respect to coordinate system. So let's write this I1 is equal to trace of metric stress matrix, which is nothing but a sum of diagonal components. Okay, I2 is the second invariant. This is first invariant, then second invariant. Okay, we can write it something like this. Okay, and I3 is third invariant, which is nothing but determinant of stress matrix. Okay, so this is our stress matrix, and we take the determinant, that is I3. Okay, so let's understand like why these are called no invariance of stress matrix. Okay, we said like what is invariance, that it is nothing but it is they do not change with respect to coordinate system. So let's try to understand this. uh, okay, let's take this is a stress state. Okay, this is a stress state. Okay, we know the stress components. And this is with respect to XYZ coordinate system. Let's denote it as a sigma I j. Now, no, let's transform this coordinate system, or let's no, find the stress components with respect to another coordinate system. Okay, or we can say like let's no, rotate this coordinate system x dash y dash z dash. So about this coordinate system at this point, okay, the stress will change. Okay, some stress components, and let's denote this as a sigma I j dash. Okay, dash means this stress matrix or stress components are with respect to x dash y dash z dash reference coordinate system. Okay? And this is with respect to original coordinate system or global coordinate system. Let's take original coordinate system. Okay, so now we have two stress state. Okay, one original coordinate system, other is no, rotated coordinate system. Now now we can say that, okay, the stress state does not change with respect to coordinate system. Okay, reference coordinate system. What does it mean? It means that uh, the impact of stress doesn't change. Okay, impact of stress doesn't change. Okay, not change, but it representation changes. Okay, the representation of stress matrix or representation of stress state changes. Okay, that means in this coordinate system we will have particular stress component sigma 1 1 2 2 3 3. Okay, you can understand this one too. Okay, and all. And in this coordinate system our stress components will be, let's say, some dash. Okay, that means the stress remains, it is the same stress, but now it is represented in different coordinate system. That means obviously the stress at a point cannot change. Okay, otherwise the deformation and strains are also changing. Okay, so that's what we are saying, impact of stress doesn't change. Okay, it is the same stress. Okay, same stress means the point is experiencing same uh, stress or deformation and strains. Only the thing is its representation is changing, the matrix terms will change. Okay, so that's what we are saying, stress state doesn't change with respect to coordinate system. Now we are talking about invariants. Okay, now let's take these two coordinate system. Now we have this stress components and these nine stress components. When we find I1, I2, I3, we can find, right, these are the invariants, okay, of the stress matrix. Okay, so from this we can find I1, I2, I3, and from this we can find I1, I2, I3. Let's take these are I1, I2, I3 dash. Okay, so this is what it means. Okay, these two are equal. Invariance means the stress representation is changing, But when you find the invariance from this stress matrix and this stress matrix I1, I2, I3 and I1 dash, I2 dash, I3 dash, those will be equal. That means I1 equal to I1 dash, I2 equal to I2 dash, and I3 equal to I3 dash. That means even if the stress representation is changing, there are some quantities of that stress matrix, okay, do not change even no, when we change the coordinate system, and that is called invariance of stress matrix. And you could have observed this in your FEA, right? Like uh, let's take example in FEA. You would have done this. Okay, let's take we are analyzing some cylindrical structure. Okay, and we got the stresses results. Okay, stress plot we got. Now we get the stress components as something like this: sigma 1 1, okay, sigma 2 2, and sigma 3 3. This cylindrical component is placed in coordinates, global coordinate system, something like this. Okay, now we may not be interested in no stresses in this orientation. Okay, so what we do in FEA, we create a local coordinate system and plot the stresses in that coordinate system. So what we do, we create a local coordinate system, some which is oriented something like this, okay, x dash, and other two in plane of this cross section. Okay, so this one and this one. Okay, so y dash and z dash. So x dash becomes axial, right? Axial stresses. We might be interested in axial stresses, so we create local coordinate system such that x dash orients with respect to axis of this cylindrical component. So that's what here we are doing. Okay, here the stress is not changing, only its representation is changing. Okay, now here we will have sigma 1 1 dash 2 2 dash, sigma 3 3 3 dash. Okay, the here we have sigma 1 1 2 2 and 3 3 and other shear stress components as well. So here these stress components are changing, but the impact of stress is not changing. Okay, and that's what we are saying. The stress state does not change with respect to coordinate system. Its representation is only changing. And if you notice in your FEA post processing, okay, even if you do, some softwares give invariants as well as outputs. Okay, in your output variables, so we can see that the invariance will not change. Okay, even if you plot the you know, stress output in local coordinate system. So hope this invariance concept is clear.